Hello everyone and welcome back to PC Retro Programmer. In the past few videos we've been trying to figure out how to draw general ellipses. So that's just basically ellipses that are rotated, and we want to do this on the original IBM PC, which has an 8088 CPU with 16-bit registers and with the original IBM CGA Graphics Card. But before we can get there, it's a pretty difficult task and might not even be possible. We need to have some way of testing out ideas for the algorithm to see what actually works. And this is a bit complicated because we eventually want to write things in 16-bit assembly language so we can run it on the CPU. But it's going to take a lot of work to iterate on code and ideas if we're writing everything in assembly language. So I've come to the conclusion that I need to somehow set up something that kind of mirrors what happens on the PC. And I'm going to do that in a programming language called Julia. Now, it's about as far as you can get from assembly language. It's a really high-level language. It's a lot like Python in that respect. And it is very fast. It has a JIT compiler, but it'll be quite different to programming in assembly language. It'll mean that we can iterate on ideas very quickly, but there's also some other features of Julia that make it particularly useful for this sort of thing. So the one I'm going to show in this week's video is how I set Julia up to draw pixels on the screen in a kind of 320 by 200 array, similar to what we have on CGA Graphics Card. And in later videos, I'm going to show how Julia enables us to test the arithmetic that we need for drawing an ellipse. So in particular, Julia allows you to set the size of the integers that you're going to be working with. It has a uint16 type for unsigned 16-bit integers and a uint32 type for unsigned 32-bit integers. Now, our CPU just has 16-bit registers, but I think we're probably going to need 32-bit integers. We'll have to figure out exactly how to do that on a 16-bit CPU a little bit later on. But it is possible, and for now I just want to know, can we do everything in 32-bit registers if we had them? So that's the basic plan of attack for the next few videos. So let me get stuck in and show you how I set Julia up to draw pixels on the screen, and presumably this could be of interest to other people who want to write their own code and want to test out ideas and need a nice high-level language. Don't be put off by what you see on the screen at the moment. This is just a bunch of boilerplate that I copied from the website for the graphics library that I'm going to be using. And actually the code for the ellipse itself will look very much like pseudocode. Julia has this very nice property that its code is very easy to read when you're just doing basic arithmetic like we're going to be. So let's get stuck in and take a look at how this works. The reason that I'm doing this, by the way, is I think there's a tendency on YouTube to just show the flashy end result. It's a lot more entertaining, but it's also a lot less informative, and people go away with the impression that you just sit down in an afternoon and out it all comes. And that's definitely not going to be the case with a project like this, where we have to look at the algorithm, we have to plan what kind of integers we're going to be using, and maybe we want to iterate on our design rapidly before we get to an end result that will code up in assembly language. So in Julia, I'm going to be using this library called Simple Direct Media Layer for the graphics, also known as SDL. You've probably heard of that. And I'm just importing it here using the using statement. And it's the libSDL2 part of this package that's got the functionality that we need. So I found on their GitHub repository, they recommend basically going to the SDL website to get documentation on all the functionality. It's normally done using the C programming language, and we're going to be doing it using Julia. And I don't really find that very helpful. I prefer to have something that's going to show me what the functions are called in Julia. And so I actually just opened the package, and there's only 2 files in the source directory, and one of them clearly contains all the functions that I can access with all the Julia types and so on. So this is what I looked at, and that's basically all the documentation we have. The only other thing they give there is a sample program on their main page, and this is actually what I started with here, and I've just modified that a little bit to basically just following my nose to do what I want. So the first thing I'm going to do though is to show you how I installed this in Julia itself. You have to install the package. And so the first thing was to install Julia, and that's as easy as going to the Julia language website and just download their 64-bit Windows binary. Now I picked the Windows binary instead of the Windows subsystem for Linux binary because I think the WSL, Windows subsystem, is basically a little bit more tricky to get working with a graphical output. And so doing it natively on Windows is much easier. Basically, you just have direct access to Windows then, and that's certainly what we're going to need here. And when I installed Julia, I set it up so that Julia itself would be in my path statement. It gives you an option for doing that. And then when I run Julia from anywhere on my machine, it would just start up immediately. So to install a package on Julia, they have this special package mode which you access with the right square bracket. So it just goes into package mode, and I should be able to scroll up through the commands. Unfortunately, it's not going to show me the package commands, but basically what I did is just add, and I think it was simple direct media layer, if I remember correctly. And this installs the package. I can do that again here, it won't mess anything up. It's already installed, so it's just going to tell me that nothing needs to happen. But you can see that it's all automated. Basically, it has a whole list of things that it'll go through and install for you in the background. It's not going to do that here because I've already done it. And that just worked flawlessly for me. The hardest part was figuring out how to get back out of the package mode, and it's just the backspace key. So now basically I'm ready to write some code, and because I've set Julia up so that it'll run from anywhere on my machine, I can put the code anywhere. So I just put it in a folder which I called Julia, and I wrote a program called Ellipse.jl, which started off being just exactly what you have on the example program on the SDL GitHub page. And so basically all I'm going to do from there is just modify that to do what I want and just look through the functions that are available, things like drawing boxes and circles and ellipses, well, not general ones, and you know, everything else that I could possibly need, and basically just put together a program in Julia that mirrors what's going to happen on the PC. And when I'm ready to run that, I'll actually be able to run it from the command line. Basically, I'll be able to do Julia, I called my program Ellipse.jl, and when I run that, it will actually run the code that I wrote. So let's take a look at the code itself and see how that works. Now, this code doesn't have very much to do with ellipses at all just yet, but we'll refine it over the next few videos until it does, and we'll actually draw ellipses in Julia using this package. So the first thing that we do is to just initialize the library, and I don't know what this does in the background, but we pass this option SDL init everything, which I think is probably fairly explanatory. Initialize all the things. Now if there's an error from that, it'll print an error message and it'll get the explicit error from the SDL package to print, but hopefully that won't happen for us. Everything's going to hopefully go according to plan. So the first thing that we need to do is to set a window up. So this is basically a Windows window, and we're going to call it Ellipse, and it's going to be set up in the center of the screen. I think this is probably centered in the X and Y coordinate direction, and I'll make it 1280 pixels by 800. And I picked these values because it'll be a nice large window on my screen, and 4 times 320 is 1280 and 4 times 200 is 800. So basically 4 pixels on my screen will correspond to 1 pixel on the CGA adapter. And I've set it up so that that window will actually be shown. And then the next thing is just an option whether you want the window to be resizable, and I probably should set that to false, to be honest, but this is what was there in the example code, so I just left it as it is. And the next thing that we apparently need to do, according to the example program, is to set up a renderer. And I'm not exactly sure what this does, but it looks like it just has some options to tell it how the graphics will be rendered in this window. And it looks like you can select an option for accelerated rendering, which probably uses your graphics card somehow, and well, present VSync. So I don't know whether that has something to do with vertical sync, as we would have on the original PC. I'm really not sure what these options do. It doesn't matter, not really very interesting for us. The next function is going to be the one that will be the most interesting for us, and this is one that I wrote. It's a little draw pixel routine. Now, of course, they have such a thing in the SDL package itself, so I didn't actually need to do this if I just wanted to draw a pixel. But I want to draw a very specific kind of pixel, namely one that is a box of 4 pixels by 4 pixels. Because remember that 4 pixels on my screen corresponds to 1 pixel on the CGA screen. In other words, I want to set things up so that I have 320 by 200 large pixels, each of which is 4 by 4 small pixels on my monitor. So in order to draw, we have to basically specify the renderer as an option to all of the SDL functions that we're going to be using, and they're in the Ellipse.jl part of the library, as I said. And the one that I'm going to use is this box RGBA command. Now, there are a lot of functions provided by SDL, and it actually took me quite a while to figure out which function would draw a filled box. And it looks like it's this one. So the coordinates with respect to my window that I set up are going to be 4 times the coordinates for the CGA adapter. And so I multiply the X and Y coordinates by 4, and I have to draw a little box that's 4 by 4 pixels. So the ending coordinates are going to be 4 pixels to the right and 4 pixels down of that starting point. So that'll draw me a little 4 by 4 box, and then I get to specify color, and I just set the maximum red, green, blue, and the alpha component as well. And so this will give me basically a little white box at position XY on the screen with coordinates from 0 to 319 and 0 to 199. So in other words, a screen that's 320 by 200 pixels instead of this 1280 by 800 that I specified for my window. And so this is going to be our CGA draw pixel routine, if you like. So that's how that function works, and you'll see in the main code in a minute that I actually call this. So most of the rest of the code here is actually just from their standard example. So I'll just step through it and show you exactly how this works. Now, the way this example program was set up is very typical of a lot of graphical applications. It's just a big loop. And in this case, the loop begins here. It's a while loop, and it will just keep looping this code over and over while this condition holds. And the condition itself is actually just the value of some variable that they set up called close. And what they do inside this program is, if something happens that indicates that the user wants to exit the program, then the code will actually set this variable to true, and that would mean that not close would be false, which would mean that this loop would come to an end, and so it will stop iterating. So I'll show you in just a moment where this close variable would actually get set to true. So the first thing that I did here, by the way, was just set up some coordinates. So I've got a screen of 320 by 200 large pixels, and I'm going to start off in the middle of that, and so that'll be x coordinate 160 and y coordinate 100. And if you're wondering what this try thing here is, it's a sort of standard thing in programming that when you're doing a kind of program of this kind, all sorts of things can go wrong which you didn't anticipate. And so it would try to run this code, and if anything goes wrong while running this code, then it will allow us to catch whatever the exception was and deal with it appropriately. So this is also a fairly standard thing to do in a program of this kind. So let's take a look at this loop. And now obviously inside this loop is going to be my code for, I don't know, drawing an ellipse, for example. In this particular case, I'm just going to draw a pixel since we haven't got ellipse code yet. But before that happens, there's this bunch of code here. Now what's happening here is it's polling for an event. So an event is something like a key press or a mouse movement or a button click or something like that. And SDL allows you to poll for all of these things to check whether or not they happened. Now I'm not going to go through all the details here because it's really not too much of interest for us, and the code has already been written for us. But one of the events that can happen is an SDL quit event. So this would happen, for example, if the user clicked in the little X at the top right hand side of our window. And that would mean they wanted to quit the program. And what happens is that an event gets triggered, and this event type here gets set to SDL quit. And so that means that we now know the user wants to quit the program. And if that's the case, then there are two loops that we need to exit from. There's the inner loop here, which is polling for an event, and there's this outer loop here, this while not close loop that I talked about. First of all, if I set close equal to true, then not close would be false, and that would finish this loop. And to get out of this inner loop here, we can use a break statement. So that's basically all this does. It's just a way of basically getting out of all of these loops, and then we can exit the program. The other type of event that could happen is an SDL key down event, and that means that the user pressed a key. And this is something else that we also care about. And we can get the scan code. It's really a lot like assembly language here, dealing with a scan code and so on. We'll get the scan code of the key that was pressed, and we'll deal with it. And of course in SDL they've set up all these constants that correspond to all the different keys that can be pressed. So for example, the W key would have scan code SDL scan code W, which is a bit easier to remember than whatever number it is in assembly language. And if that was pressed or the up key was pressed, then what's going to happen is it's going to subtract 1 from our Y coordinate, and it'll loop and draw another pixel, and that'll have the effect of drawing a pixel that's 1 up from the previous pixel. And there's various events for other key presses. Looks like the W, A, S and D keys are used basically to just move the pixel around on the screen. And you can use the cursor keys as well. So that's pretty nice functionality that we can play with. And I also added this one in here. If the scan code was for the escape key, which probably doesn't work on all platforms actually, but it'll work on Windows at least, then that's another case where I want to set close equals true and to break out of that loop. And the reason that I did this is because I don't really know whether other people have a screen that's quite as big as mine, and so this 1280 by 800 small pixels that I set it up for might be a little bit large for some people's monitors, and they might not actually be able to get to the X in the upper right corner of the window, so they need some other way of exiting the program. At least on Windows they can press the escape key. And if there wasn't any event at all, then it'll just break out of the polling loop and move on. So that's all pretty standard stuff. It's mostly boilerplate. But let's get to the program itself. Now, the first thing we want to do is that if the x-coordinate gets too large, so greater than or equal to 320, that would be off the right-hand side of the screen, then we'll set it back to 319, which is the last pixel on the screen in the x direction that you can actually see. And if it's less than 0, we'll set it back to 0 so you can see it. And same for the y-coordinates. We'll just make sure they're in bounds as well. And then the next thing is to draw a pixel using my pixel drawing routine. This is a big pixel at coordinates x and y, and it'll do it using this renderer that we set up in the beginning of the program. So that's basically all this program's going to do. It's just going to do a big loop, check if a key is pressed, change the coordinates if necessary. If a key was pressed that indicated the user wanted to move the pixel around, and otherwise we'll just let you quit the program. So I don't know what this line actually does here. I didn't bother commenting it out. I think that this just displays on the screen whatever has been set to render. So you can, as far as I know, have a whole bunch of things rendered, and then when you're ready to present that to the actual device, so to the monitor for display, then I think this is the function you call. And then there's a little delay. This is just so that the program doesn't run too fast, and that's the end of the loop. And this is basically what will happen if there's any kind of error, and also this will happen once this loop exits. So it will destroy the renderer, it will destroy the window, and it will quit SDL, which will also be the end of the program, which will quit to DOS. So pretty straightforward. A lot of that, I would have had a lot of trouble figuring out how to do myself. So I'm glad there was an example program here to show how all of that works. But let's actually take a look at this program working. As you can see, it's not going to do very much. It's just going to display pixels and let us move them around on the screen. And all the fun is going to be in writing an ellipse function here, which will call this draw pixel routine, and it will do all the arithmetic inside the ellipse function. And instead of drawing a pixel every time this iterates, we'll instead be drawing an ellipse on the screen. So that's what we're going to aim for, and that's what we'll have in future videos. But let's see this running and see where we've got to so far. So to see how our program actually runs, we'll go back to the command line. You just type CMD into the search bar on Windows, by the way, to get the command line. And then I just type Julia Ellipse.jl, as I mentioned previously, to run my program. And it'll take a couple of seconds to start up. Well, after fiddling around with the video settings a little bit, you should actually be able to see this now. Actually, on my screen, I see a window. You're just seeing the contents of the window. I can actually see a little thing that says ellipse in the upper left-hand corner, and in the upper right-hand corner there's a little X for me to exit the program, but unfortunately my video recording software doesn't show you that. But it is there, and in the middle of the screen we have our large pixel, exactly as expected, and if I press cursor keys, it moves it around. So it all seems to be working, and given that most of the code was just from an example that I've modified, it really wasn't too difficult to do this. And it gives us a way of doing graphics that's very similar to what we'd be doing on the PC with a 320 by 200 screen. And now all we need to do is just focus on the actual arithmetic for drawing the ellipse itself, so figuring out what the coordinates of the points should be, and then just calling this pixel drawing routine over and over again. So in the next video, we'll set it up so that we actually compute those 8 special points that I talked about in a previous video. Those are the starts of the 8 arcs that we need to draw our ellipse. And we'll get that working, and then the following video hopefully we'll get code for actually drawing the arcs themselves. So let's just confirm that if I go to the top of the screen it won't let me go any further. Yeah, that's all working. And if I go to the left it'll stop there, so that's all working. So everything seems to be going exactly according to plan here, and hopefully this gives you an idea of how you can do experiments before actually diving into assembly language for a final project. And yeah, I think we're going to get a lot of value out of this. One final thing to check is that if I press the escape key, it will exit. Unfortunately, it's not going to show you the command line again, since I'd have to fiddle around with the video settings, but indeed it worked for me. So look out for the upcoming videos on this, and we'll try and get ellipses drawing in STL and Julia and figure out how our algorithm's going to work.